this thing. Yeah. In 2 hours? 2 hours? I'll be ready in 2 hours. No, no, no. So I guess that everyone is all ready to just completely switch subjects. So forget what you've been listening about. You'll have to remember again in the afternoon, of course, everything. And we're going back to resurgence on the asymptotics. So we've, until now, I've showed you a very simple example, second order linear ODE. We had two exponentials to, meaning I showed you how you could in principle see that one of the exponentials, if I studied in the Borel plane, meaning, so we also saw that if I did optimal truncation, there was the error, and there was at some point in the complex plane, if I study analytic continuation in the complex plane, that at some point I had to pick up a second solution in order to actually have the correct result all throughout the real axis in the Airy function. We saw like how this gets picked up from the Borel point of view, Borel plane point of view as well, and also an explanation of why that picking up that solution came with a very specific number, which was I. So now I want to go a tiny bit more general, but so meaning there's a whole mathematical structure in the Borel plane, of analysis in the Borel plane that you can do, and this came from originally this came from the meaning nonlinear ODEs. So not just even linear, nonlinear ODEs. You can do this you can study this whole structure quite accurately, meaning prove it and all these things. We're not going to prove things. We're just going to see them appearing. In physics, I would say, amazingly enough, even when you don't have nonlinear ODEs, often all these structures are still present. And you can still study the problems using the same type of structures, even if you don't have the whole backing of the proofs that come from nonlinear ODEs. But in this particular case, I will be talking, so what I'll be showing you now is a nonlinear ODE, first order, to make things very easy. Meaning this is a problem that has been thoroughly studied, including with resurgence, and it comes from relativistic hydrodynamics. So basically, what happens is that you have some system of a strongly coupled fluid. This tries to mimic what happens in quark-gluon plasmas, where you have a very highly non-hydrodynamic regime at early times, and then the system thermalizes and kind of you start being able to use effectively like the theory of hydrodynamics, relativistic, in order to study the system. And the idea is how does that happen? And there's a few different models that do this. One of them is called MIS, Mueller, Israel, Stewart, and basically there's different. In order to actually get the equation that we have to assume conformal symmetry. We have to assume like a lot of symmetry in the system, of course, because otherwise you wouldn't get a single nonlinear ODE describing the system. But just to mention that this is the typical thing that you're trying to describe. This is a toy model to describe it. And let me just write the nonlinear ODE. So I'll explain what these are. So this function f is describing the effective temperature, energy density. So there's only a single function that I have in my system. Depends on proper time. In fact, it's meaning another thing is the pressure anisotropy. So it measures the anisotropy in the system. Sorry. So it's a complicated, meaning complicated. It looks like a long equation. The only reason I'm writing it is just because it actually comes from a physical system. Otherwise, we could use, sorry, plus 16. Sorry, yeah. Over 9 minus 2z over 3 equals to 0. So what do I have? I'm assuming z is basically proper time. F is pressure anisotropy, but again, you can think of it as just a measurement of the energy density, and the C's are transport coefficients. So in the end, so I want to describe, I know that at late times, the system is described by hydrodynamics, by viscous hydrodynamics. So the shear stress tensor in the energy momentum tensor will have some transport coefficients, and these coefficients are given by this. These are going to be numbers, so there's a whole connection with the fluid gravity correspondence where these numbers actually have specific values. In the mathematical file, that's what I'm going to use. But in any case, for our purposes, this is a first order non-linear ODE. You can see there's an f squared, there's an ff prime. And what we're interested in is the behavior at late times. So the behavior when the system goes into a hydrodynamic regime. And in particular, if you did some studies, meaning if you solve this equation numerically, what you'd get is like different solutions. At early times, you have very different solutions. They diverge, except actually one. There's one, that pink one, which is actually finite at time t equals 0. But one thing that you can really see is that they all go to the same value at late times. They all slowly, meaning not slowly, quite fast, converge to a single line. So this is what's called the hydrodynamic attractor. Well, actually, the pink line is the hydrodynamic attractor because there's also a behavior finite behavior at early times. But the other point that I wanted to make is that, what people have seen is that, so that line is basically a power law convergence to the ideal fluid, which would be the final point. But in fact, somehow hydrodynamics works when F, which is pressure anisotropy, like I said, it's the measurement of how far from equilibrium we still are in some way, when F is still quite large. And people started thinking, okay, why does this work in these regimes where we'd expect that hydrodynamics would still not be viscous hydrodynamics would still not describe our system? Why does it describe very late? And the main reason for it is because behind this late time analysis, there's an asymptotic series. There's exponentially small terms. So all the initial conditions actually converge exponentially fast to our power law series, which is asymptotic. And we saw asymptotic series do converge quite fast to our results. So this is the behavior. So let's, one thing, of course, when we're talking about, we saw the exponentials. In this case, we'll have exponentially suppressed terms at late times, but at early times, so if I have an exponential that is of the type e to the minus az, If z is very large, of course, this is exponentially small. But if z is close to 0, or even just small, of course, these exponentials are going to be your major contribution to the solution, which means that, of course, that very different behavior at early times is going to be governed by the exponentials themselves, while at late times, they're just almost not there. So let me, how do we, so it's a first order nonlinear ODE. We don't have a finite number of solutions. We expect exponentially small solutions to our ODE. So the first thing you can do is add an exponential ansatz, again, of this type, times some power series. Z, again, I'm assuming Z large, right? Because I'm trying to solve at late times. So phi of Z is equal to Z to the beta. I don't know what beta is, and I have Cn Z to the minus n. So I don't know what beta is, I don't know what A is, I just want, but I have a differential equation. I can just plug it in, I can calculate them. And indeed, you calculate these, this is very easy. You have beta equals C eta over C. And in fact, my solution is not just a single solution of this, it's going to be a solution where, because if I introduce an A, because of the nonlinearity, I need to introduce a 2A, and I need to introduce a 3A, 4A, because again, as soon as you start doing the product of the function with itself, if you have one exponential, you have an infinity of them, which means that in fact, what I will have is something like this. And the final solution is going to be a power series in late times, but also a sum over all the exponentials. It's like airy, but instead of 2 exponentials, now we have an infinity of them. So what is my solution? My solution is a trans series. And, sorry. I'm writing the trans series in a particular way, but it'll be clear. So it's going to be a sum over all the exponentials. In fact, each one of these comes, meaning you have an unknown parameter that can be multiplied by the same power as the exponential for each one of them. Why? This is a first order nonlinear ODE. We have an unfixed parameter defined by boundary conditions, defined by initial conditions. And then what I'm now assuming my phi n's are, my phi n's now don't have the Z to the beta. So in fact, I have that this is just AKN. So for each sector N, I have a power series. So that's so it's at infinity. It's very easy to see that this goes, meaning that if you plug this into the equation, you take Z really infinity, you have just a single constant. And you can calculate that constant quite easily. But moreover, you can actually calculate any coefficients you want, not an infinity of them, but you have recursion relations to calculate any coefficients you want. Just for completion, let me just write you, so the first coefficient that I'm saying, so this is the ideal fluid. Just to say that the perturbative series alone, just the perturbative series for this problem, gives you the viscous hydrodynamics, gives you ideal fluid plus corrections to that ideal fluid. The exponential terms are called the non-hydrodynamic modes. They're the modes that are extremely important at early times, but basically they disappear at late times. They're non-existent. So I have that, this is the leading term. So the A01 equals 4 C eta divided by 9, and now AK plus 1, 0, C tau pi, 16 over 3 AK0. So these are recursion relations. Please plug the solutions in. You'll see that you can get this quite easily. 4 minus n. I shouldn't be using n here because it's confusing with that. AK minus m, 0, A, m, 0. So these are the recursion relations. This allows you to calculate perturbative series to whatever order you want. So assume that you have, well, you can solve this perturbatively, meaning perturbatively you get a nonlinear ODE obeyed by the phi 0. It's easy, it's the same equation. That's what will give you that recursion relation. Now, assume that you have, try to put a phi 0 plus exponential of minus AZ phi 1 in it. What will happen is that if you have this, you're going to get a term that is exponential of minus 2A phi 1. Of course, to order exponential of minus A phi 1, you can solve it and you get phi 1. But that means that if you don't include an exponential of minus 2A phi 1, it will never cancel the terms that you're getting there. And then if you get to 2 phi 1, then you need the next one, the next one, the next one. Does this make sense? Sorry. So this is just a setup, again, for us to try and study what happens. Let me just, one moment. My brain is still geared at modular forms as well. So one thing that we can do is just study the universal behavior. Remember, we're talking about a trans series. It has exponentially small terms. Are the sectors phi n that I wrote here related in the same way as we saw that the Airy function was related? We should expect that universal behavior of factorial over power with terms, coefficients that show up. So we can generate lots of terms, and what we're going to see is that AK0 for K large, again, these are large order relations, right? So K large, this behaves as K minus beta divided by A K minus beta. Then there's going to be some constant, and then there'll be a behavior like this. So first thing to do, generate data. Plot K plus 1 divided by K. AK plus 1 divided by AK. And I think so I've meaning just to mention, so this is just giving some values to these C's and generating data. So I have here exactly what I've mentioned. So I have just the series that I just wrote, right? Can I? Yes, here. Is that better? So just to say that, yeah, so here I'm just defining the coefficients and calculating them. Here I'm calculating 100. And just putting the numerical value because again, I can calculate this to any accuracy I want, but mathematics is much better at dealing with numerical values than not. So, meaning, again, don't think them as numerical. You have infinite accuracy if you want. But, again, to do plots, we don't need infinite accuracy, so it's easier to do this. So this is what it does. And if you plot AK plus 1 divided by AK, this is what you get. Go figure, we have a factorial growth, right? Because if I have an AK, so if I assume this universal growth, and I did AK, so in the other one I have AK, so let me just do AK divided by AK plus 1, just because it's, instead of growing, it decays. So if I just plug this expression exactly in my AK divided by AK plus 1, and then expand for large K, what do I get? For the A, I get some A here. From the K minus beta, that's going to be an interesting thing. I don't know if I get an AK minus beta or an AK plus beta. Do you? I always get confused. If I have here Z to the beta, do I get a minus beta there or plus beta? I would have to check again. Meaning the only way to check is actually do the calculation I did for the large orders, and you get the exact coefficient, but I don't remember. But here I seem to have assumed that it was a K plus beta. So I'll just make sure that I'm writing here plus or minus. I'm not exactly certain, but let's assume it's a plus at the moment. So this is A divided by K plus beta. And then, so if I had here, instead of the O, I have D1 over K plus D2 over K squared, meaning it's the expansion in 1 over K. What I have here, of course, it's sum in L dL over K divided by sum dL divided by K plus 1. Sorry, K to dL. K plus 1 to dL, which I can also expand, right? So I expand now this for large K. And very easily, you'll find that this is A over K minus A beta over K squared plus A beta squared plus D1 over K cubed, etc. So why do I care about this? I'm just trying to tell you that, as we've mentioned before, I can use these to actually, if I didn't know what beta and A were, I could calculate them. I could check them. So basically, that means that I have that AK divided by AK plus 1 times K is going to be A plus order 1 over K. So, by the way, that's exactly what I have here. And that's actually the blue plot. And you can see that there's a lot of other plots there that converge much faster. This is called, especially if you have just real values and not more than one, this is Richardson extrapolation. So you can actually accelerate your you can extrapolate you can accelerate your convergence with the methods of Richardson extrapolation. So does anyone know what Richardson extrapolation is? By any chance? No. So let me assume that I have a series Sn, which is equal to, S0 plus S1 over n plus S2 over n squared plus etc. Something like that. So I write the Richardson extrapolation of the series S of, and now I'm trying to do of order n. So the order 0 is just my original series. Now, of order n, it's the, you just do it. So it's n plus 1, n minus 1, plus n over n. I'll just do an example quickly. So this is, you can define this, so you define this recursively, of course, 0, 1, 2, 3, etc. But, for example, if you do n equals 1, and you calculate the RTS of n1, and I'm not going to do it, but please check. You can see that for n large enough, if you do this analysis, for n large enough, what you get is S0 minus S2 over n squared. Can you see what it's doing? So if you calculate the second one, it'll kill off the n squared term. You'll keep an n cubed only. It keeps on killing the terms, and basically that's why it gives you an acceleration. You keep S0 plus order 1 over n squared. The next one, it's order of 1 over n cubed, etc., etc. And that means that actually your convergence to your whatever original value you're trying to find, which is A in our case, is much faster. So, as was mentioned also previously, you can also find a convergence. I mean, you can find beta. So I wrote there that it's a over k minus a beta over k squared. I can find k. How? Well, you can do, for example, ak over ak plus 1 times k minus a times k again. And what you get is the a beta term. So if you do k minus a, this will be beta. You can also directly find sums and subtractions of the a's such that you get directly a beta. So it's exactly equivalent. Again, you can do this, obtain your value of beta. So this is what I'm having here. That's the, so in yellow, in both of these in yellow is the actual value of beta because I know what it is. I can calculate it from the differential equation, but I'm just stating that you can also obtain it, and you can obtain it with quite high accuracy, in fact. So this is perturbative series. I got yay, the beta. I could get the coefficients d1, d2. From the area example, we know that these coefficients should be related to the first exponential. But in order to see that, we need to calculate the coefficients of the first exponential. Well, we could use this to calculate them, but when we have a differential equation, we can calculate these. We can check that these results are all equivalent. So how do you do that? You just plug in the ansatz into the differential equation, and let me just write to you. So for, if I did phi 1, so meaning, let me tau pi, I can write this. For any series you have phi m prime minus ma phi m So this is just plugging in and keeping separating each exponential order. One thing I wanted to ask is, can you see that this expression is very different than the original equation, or moreover, the equation for the perturbative series? This equation is a linear differential equation whose particular solution depends on the previous ones that you calculated. So just to mention, and you can do this for each L and calculate the coefficients, you get recursion relations, et cetera, et cetera, et cetera. So, I forgot one mention. Again, the S1, remember the S1 was a very important. The S1 over 2 pi I, it was whatever we got that the series jumped for. How do you calculate it? You calculate it by doing AK0 divided by gamma of k plus beta times a to the k plus beta. And this is going to be your S1 over 2 pi I. And again, you can do Richardson extrapolation and find your result. And in this case, you get, I can't remember, S1 4703I, something like that. It's a number. Doesn't matter, it's a number. But so now what I would like to do is to try and understand the relationship, let me just check, the relationship between the different sectors. And we've seen that, you know, we have large order, we have everything, but what we really want is to find, in order to actually calculate, you know, the things properly, we want to find the Borel transforms. We want to find the behavior of the singularities in the Borel plane. So now the question is, how can we do this? Well, we have our phi ends. They're our asymptotic series. Yes. It's not the same if you change, meaning this is particular values of the transport coefficients. Yes, 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 yes.
Do you know that the
I never even checked, in fact. I've used different values, and I know that I calculated different Stokes constants, so I know it depends. But I haven't checked the relationship. You have two transport coefficients, so I don't even know, given that I've never even tried to do an analysis of each one separately, in fact. One scales out. No, but with when you have, because here I only put 2 and there's 3, does that always happen? Okay. So what is the Borel transforms of these? So meaning to solve it to all orders.
Yeah, no. Like getting an analytic function.
You can get some analytic functions later on with summations, but not. So for the thing is, as we'll see next in the next thing, is that if you sum over all the exponentials, you actually get a finite function, meaning an actual function. But summing, but for the AKs for each order, no. So 1 second. So this is I guess what I'm going to say is a tiny quirk, and I haven't mentioned some of the properties of the Borel transform. I will do so in a moment. But I know that my perturbation series grows as factorial of n plus k. Calculate the Borel transform, I can in fact just divide by a factorial growth. But then I'm not dividing by the exact factorial growth, right? Because I know that factorial growth is n plus k, and if I divide by n factorial, which is the natural thing, I wouldn't get. And let me say that it's convenient. And the reason why it's convenient is that actually, if you do have the exact factorial growth removed, in the Borel plane, you end up with log cuts. And so what I'm going to do is to define, I'm going to do z to the minus beta. Because if I do this of t, this is the Borel transform of sum k greater or equal than 0, ak0 z to the minus n minus beta of t. And the Borel transform of this, if you can calculate it, is just the sum over k greater or equal than 0, ak0, t to the n plus k, and at n plus beta minus 1 divided by gamma of n plus beta. So this is what you get. Again, like this, I'm actually dividing by the exact factorial growth. This is just, and now we come to, I'll stop a moment and state, let me just see. And state something. So I just multiplied z to the beta for phi, and I got this is not just a multiplication, right? So what happens in our physical model and what happens in our Borel plane are very different behaviors, right? So typically, when you talk about this, you talk about the physical model as the multiplicative model and the Borel plane as the convolutive model. And there's ways of knowing what you do in one, what corresponds to the other. And I'm going to just give a little aside on this. Which is so the Borel transform typically takes, goes from the power series, in this case, when I'm taking Z large, the power series in Z, as I've mentioned before, we should start as not with the leading power Z to the 0, because that, with the Laplace transform, has some issues, but you can say that the Borel transform goes from, it's typically this, power series of Z to the minus 1, and it goes to the complex plane in S. And how do I, so if I have some series, so of course, meaning here, if I have Borel phi of Z, I want to have here the Borel of phi as I've defined before. Of S, so actually I was using T here, so let's use T. How does it go? power z minus alpha minus 1 goes to t to the alpha divided by gamma alpha plus 1. Some things that are quite important. So derivative of phi, and I'll explain to you why this is important in a second. This goes as minus s Borel transform of phi. Minus t, sorry. Why do we call multiplicative and convolutive model? If you have two series here, phi 1, phi 2, multiplied, what you get here is Borel transform of phi 1 convoluted with Borel transform of phi 2. And what I mean by convolution is the usual integral from 0 to t dt tilde gives you the convolution of the Borel transforms. And of course, as we saw, multiplying, meaning this is just one of them, but z times phi goes here, sorry, to the derivative of Borel, the Borel transform. So just, there's a couple more, but the main things that we're going to use here are these. So another question that now I have is, I said that I wanted to calculate these. Like I said, I multiplied here. This is the behavior that I end up getting. It's quite important to know this behavior. But I don't have all the AKs. So, meaning, how do I analyze this? How do I analyze my Borel transform if I have a series? I know the series is finite radius of convergence, but I need to understand the singularity structure. So what typically one does is approximate this by some method, and one of the methods is calculating Pade approximants of the Borel. And what's the Pade approximants? The Borel Pade of some order n of phi of t is given by sum equals 0 to n over 2 a n t to the n. So it's a polynomial divided by another polynomial. Such that, of course, if you expand for small t, you get the exact coefficients of your original series. So you can calculate these coefficients. Or you can just ask Mathematica to do it for you. Because if you calculate the Pade approximant of a series, it will give you directly the Pade approximant. So if you do the Pade approximant, let me just, if you do the Pade approximant of the Borel plane, in the Borel plane, it gives you the analytic continuation of your series, and it will have singularities. Of course, it will have pole singularities while we expect log cuts. What does that mean in effect when you're analyzing this? It means that you have a condensation of the poles at some points. And so this is what happens if you do the Borel Pade of the original series. You can see that there's going to, meaning the value, for the values of the transport coefficients that I tried, this is my action A. So it starts at A, and it has a condensation of cuts there. It looks like it has one cut. So what can we do to see if, in fact, because this is a nonlinear problem, we expect an infinity of cuts. But the problem is that they're on top of each other. So in fact, what I would expect, if I could change the position of the cut, is that they would have cuts at A, 2A, 3A, 4A, all corresponding to each one of my sectors in the trans series, each one of my exponentially small terms. But I can't see it here. So one way of dealing with this is doing conformal mapping, doing a conformal transformation. And I wanted to just mention this because it's actually quite useful to know. So once we have the Borel transform, if you do a transformation, so this is conformal so what you do is like you take t equals minus 2az, something weird happened, minus 2az divided by 1 minus z squared. And what you're doing is mapping the singularities. So, sorry, this is, again, just trying to understand the different thing. And you're mapping the singularities that you had to different points in a radius of a circle of radius 1. And basically, what you have is you're mapping t equals 0 to z equals 0. T equals a to z equals plus minus I. T equals 2a to z equals 1/2 1 plus minus I square root of 3, and etc. So what you're actually doing is mapping these, and you can indeed see that you have extra singularities, meaning, of course, the more terms you have in the Pade approximant, the more terms you would also see this. There's even better ways of seeing the singularity structure, but this is an easy way to see whether you actually do have extra cuts or if it's a single cut. So, and what I wanted to say is that indeed the general singularity structure that you expect is something like that. So you'll have cuts at phi that are associated to the sectors phi 1, phi 2, phi 3, phi n. So, but we're doing the perturbative series. What would happen if I analyzed, instead of analyzing phi 0, I analyzed the Borel transform of phi 1? What type of singularity structure would I expect? So for phi 1, and this is what it's written here. So if I was looking at the point phi, at phi 1, so at the singularity A, phi 0 is on the other side, but phi 0 does not, is the perturbative series. It's an honest perturbative series. There's no cut associated to it. So you'd still have cuts at A, 2A, 3A, as seen from phi 1. But something, so, and you have an infinity of cuts. But for example, if you looked at phi 2, now phi 1 is on the other side. So then suddenly, if you did the Pade approximant and you saw the cuts, you'd see cuts, an infinity of cuts on the positive real axis, but you'd see also one cut on the negative real axis associated to phi 1. So the whole story that, so of the two Airy solutions that one sees the other one sees the first, this is also true here. Phi 1 sees the other ones. Phi 2 sees phi 1 backwards and the other ones forwards. So there should be large order relations that kind of give you this whole behavior in some way. So yes, so like phi 3 would have cuts phi 1, phi 2 on one side, and phi 4, phi 5, etc. on the other side. So how do I express this from the point of view of the Borel transforms? What I'm saying is that the Borel transform of a sector phi n of t at some t equals ka is going to have some constant, and now this, I'm writing it slightly different. It's a constant here. This is not the Stokes constant. This is a function of the Stokes constants times the Borel transform, of phi n plus k at t minus ka. So this is at 0. If I'm looking at t equals ka, this is at 0, times a log, so this is a log cut. So there's no cut at 0 for the Borel transform phi n, right? So this is finite radius of convergence. But there'll be cuts all in towards the positive real axis, but there will also be cuts in the negative real axis associated, but in finite number, because it's associated to the previous ones that we had. So these Sn, n plus k, I'm calling it the Borel residues. They're like residues in the Borel plane. And they're directly associated to the Stokes constant. So we're slowly building towards alien calculus. In particular, what can I use this to calculate my S? So I know that I have a Stokes line in the positive real axis. I have singularities in the positive real axis. So can I calculate the lateral the lateral resummations for my sector phi n? So I said that I had cuts starting at A, starting at 2A, starting at 3A, etc. And what I want is so this is the S plus, this is the S minus. So I want the difference between them. So I am just, so what I would get is sum, sorry. And I'll write what the CKs are in a second. And this are if I have the cuts here, then I can have contours going around each one of the cuts. So this would be the C1, C2, C3, C4. By the way, we do have cuts for K less than N, but I am calculating the jump across the positive real axis, right? The Stokes line at 0, not in the negative real axis. So this is just so again, this is quite important. It's a detail, but it's quite important that I'm writing this with an S minus. Again, I just told you that all the phi's have singularities in the positive real axis. So I can't resum in the positive real axis the phi's. I have to choose a lateral resummation always. So this is, because I'm writing the minus, because actually the plus minus the minus is related to the minus summation of each one of them. Of course, you can calculate then for each one of them the plus minus the minus of each one of them continuously and write them just in terms of a single thing. But I'm just saying that all of them always have, because we have an infinity of exponentials, they always have a discontinuity. So this is by definition minus S, we defined this yesterday, the discontinuity across the positive real axis of my phi n. So again, I'm not going to write, but one can do this also for the negative real axis, and it's quite important. For example, for the large order relations, you're going to get large order relations on both. So you'd get so that the discontinuity of 0 of phi n is then the sum of Sn to the n plus k e to the minus z ka phi n plus k. And the discontinuity, you could do the same thing, discontinuity at pi of phi n greater or equal than 2, because the other ones don't have, is equal to sum, and this is to infinity. So this is k equals, sorry, k from 1 to infinity. Here is from k from 1 to n minus 1. Sn goes to n minus k, e to the z ka phi n minus k. So I wanted to write the discontinuities because these discontinuities are directly related to what is called the Stokes automorphism, which allows you to define now a different type of operation, which is the derivation, which basically allows you to apply this directly in the trans series and try to understand a lot of the information directly from the trans series. So these are my discontinuities for my first order nonlinear ODE. I have now a definition, which is like that the operator 1 minus the discontinuity at 0 is by definition what I'm going to call the Stokes automorphism at 0. And it's a Stokes automorphism because it can be written as exponential of something that is called a directional differentiation. So it's a different, in this case, it's in the direction 0. It could be in the direction theta. And more particularly, this can be defined, can be decomposed into components that depend only on the singularity points in the Borel plane, along the direction theta. Again, this is always in a particular, if there is no singularities in the Borel plane in that direction, what you have is that discontinuity is 0, means that the Stokes automorphism is just does nothing. It's the unitary matrix, so it's nothing. But here, what we have is that this can be written as exponential of, in our case, sum n greater or equal than 1
e to the minus NAZ delta AN. Why AN? Because those are our singularities along the positive direction. It's A, 2A, 3A, 4A, etc. So somehow these are derivations in the sense that, so they're honest derivations. They obey the Leibniz rule. So if you apply them to functions, to product of functions, they obey the Leibniz rule. And these, so in a direction theta, what you have is that the Stokes automorphism is typically written as exponential of sum of the omega i's along the singularities in that direction theta, e to the minus omega I z delta omega I. And these are called alien derivatives. So alien as, I never liked it. Alien as foreign, right? Not alien as from outer space, because it comes from the French of the calcul étranger, and it's alien as foreign. So can we now understand our, what I call the Borel residues from the point of view of the alien derivatives? And now, so what we have is that sum of k greater or equal than 1, Sn goes to n plus k, e to the minus z ka phi of n plus k is equal, using the definition of the Stokes automorphism, it's equal to 1 minus exponential of sum k greater or equal than 1 zka delta ka acting on phi n. I can expand that exponential, and what I get here is minus sum k greater or equal than 1 over k factorial, sum n greater or equal than 1 e to the minus z na delta na to the k acting on phi, sorry, let's use here phi m acting on phi n. And now I can match exponential weights on each side. And if I match exponential weights, what I get is that delta A of phi n is equal to minus Sn goes to n plus 1 phi n plus 1. Delta 2A phi n plus 1/2 delta A squared phi n. By the way, the delta A's don't commute. Delta A, delta 2A is not the same as delta 2A, delta A. So one needs to be careful about that. Phi n is equal to minus Sn n plus 2 phi n plus 2. And then on, and then on, and then on. So you can, from here, you can calculate the delta 2A directly because we know what delta A is. So we can act with it twice. And you obtain all of the delta NAs in terms of Borel residues. Why? Meaning, yeah, I have still a little tiny bit. I didn't stop. Daniele, I didn't stop.
Continue. Sorry, I didn't realize the time. So why did meaning, as you're going to see next, the delta, meaning there's a systematic way of using these alien derivatives to study the trans series, to study the resurgence. Because the Stokes constants, meaning while the Borel residues, when you calculate Borel residues, they're completely dependent on the sector that you're analyzing and the sector that, and the singularity that you're so you're doing the Borel transform of phi n, and you're analyzing the singularity Ka of phi n. So the Sn goes to n plus k. It's completely dependent on these two. The Stokes constants aren't. Constants only depend on this number here, a to a, etc., etc., etc. So they're actually more, I would say, more universal in that sense. But, of course, for us, in terms of calculations, it's much easier to analyze the Borel plane and check what happens at the singularity. So in terms of calculation, direct calculation, if you didn't have much information, calculating these Borel residues is the easiest way. So I just wanted to show that these two things will be completely related. And in particular, I'll show you the steps to prove it. So what I wanted to say is that, yeah, the delta NAs are in some way getting the algebraic information of the Borel transforms, but removing the functional nature. They don't care about the log parts. They don't care about anything. They just want to know how the structure, the algebraic structure works. And it can be proven. For our case, again, this depends on the trans series. It can be proven that, sorry, and, oh yes. Why did I use, this is a K. That's a K, yes. So what am I saying here? That the Ka, first of all, for K greater than 1, this is 0. So delta 2A is 0, which means that actually the Sn n plus 2 is just 1/2 of acting twice with this one. So you can see that actually these Borel residues are highly constrained. Like I said, they're easy to calculate because we have a log cut and we just can calculate what's the contribution of that log cut. But they're highly constrained by the resurgence structure, which is what this gives you. And I will show you this. This comes from what's called the bridge equations. And I think that's the last thing I want to do today. I will mention just the larger relations without calculating them. But so if you do this, so this is highly constrained again. This is specific for our first order nonlinear ODE. So for a trans series that comes from a first order problem, nonlinear. So and there's generalizations for higher orders, of course, meaning that which are not difficult. But so I just wanted to say that, for example, if you write this, Sn n plus 1 is equal to minus n plus 1 S1. And now S1 keeps on showing up. S1 is the Stokes constant. These are the Stokes constants. This is the I that was showing up in the array. This is the one that I calculated and said there was that 5.4 or something I. So this is the Stokes constant. So now Sn goes to n plus 2 is equal to minus 1/2 n plus 1 n plus 2 S1 squared. And then the Sn n plus 3 is going to be Sn plus k. And actually, the general, let me just, no, let me delete
the top one here. So I can write that yes, n plus k is actually just minus 1 over k factorial n plus k factorial divided by n factorial s1 to the k. It depends on a single Stokes constant. They're all related. They're all highly constrained. And in particular, if you write that, the discontinuity across the zero of any sector phi n is going to be just minus some k greater or equal than 0, greater or equal than 1, sorry, 1 over k factorial n plus k factorial divided by n factorial s1 to the k e to the minus k az phi n plus k of z. And I leave it as an exercise that if you do this, then you can show that for the full trans series, the resummation above of f of z sigma is equal to, remember that this is the resummation below of 1 minus the discontinuity of f, and this is S0 minus of f. Remember in the area function, across the Stokes line, what happened to the parameter sigma? Jumped by the Stokes constant. That's exactly what's happening here. Across the Stokes line, at 0, the parameter sigma, which is now our parameter in the trans series, jumps by the Stokes constant, which is a single Stokes constant in this case as well. So it's exactly the same thing. And again, you just need to use these, and you get, with the binomial theorem, you get exactly the correct sigma plus S1. So it's quite simple. The pi direction, slightly more complicated. Why? Because actually in that case, Stokes constants are different for each one of them. It's important to calculate large order relations, but meaning in terms of the actual, to understand the Stokes phenomena in this case, this is not something you need. So, nope. So phi 0 doesn't have its own parameter sigma. So in the situations where you have sigma, so if you have a perturbative series, which is actually a different sector, like in the area function, well, the area function has two exponentials, so it's not really, but look at the Bessel functions, where you have a perturbative series and a non-perturbative sector. There you have two parameter sigma that can jump separately. Here, in the nonlinear problems, the phi 0 is really just the 0th point of a whole string. And I'm meaning, mathematically, I'm not actually, I don't know how this is proven, but indeed, the phi 0 does not have a cut associated to it. That's why you never see it. Well, actually, you know what? If you if you did put it if you did put it in the bridge equations with the expansion, you'd find that it came multiplied by 0 always. So it's kind of like the delta minus a wouldn't give you anything, or delta minus 2a doesn't give you anything. It comes multiplied by the n plus k, where k equals minus n. K minus n, exactly. So it comes always multiplied by 0. So it's like it's enforced there. It's never 0. It's always 0. So can I see this from the trans series? And so
just 1 second. I just wanted to see. Just before, no, we'll finish with this one, yes. So this is the Stokes automorphism. Remember that I had written, at some point, I wrote, and I deleted already, some properties of the convolutive model as compared to the multiplicative model, meaning physical versus Borel plane. And one thing that you can see is that ddz of the resummed result of a phi is the same as resumming ddz of phi. You can easily see this by using the fact that S is just a Laplace transform and checking what happens. Because, of course, we know that dz of phi in the Borel plane corresponds to the minus S times the Borel transform. I wrote this. You check that what that corresponds in terms of a series, and you see that this is indeed true. Why do I care about this? Is because what I actually care about is that the ddz commutes with the Stokes automorphism. So ddz commutes with the Stokes automorphism. Because, again, so meaning if it commutes with yes, it commutes with the Stokes automorphism as well. Just 1 second. So what this means is that if I wrote the Stokes automorphism in the direction theta, which is exponential, do I still have it? No. Exponential of sum of the omega I in the direction of the singularities in the direction theta, e to the minus omega I z delta omega I. This means that basically what will happen is that the ddz will commute with all these operators. Not these ones, because this depends on z, but because it commutes with the Stokes automorphisms, it commutes with that. So what I'm saying is that it commutes with those objects. Moreover, as it's clear, dd sigma, where sigma is the parameter in the trans series, meaning they commute as well, meaning there's nothing special about that. And that means, actually, that if I calculate the trans series, that e to the minus omega I z delta omega I of my trans series, it'll obey, meaning if f obeys a differential equation in z, this will obey a linearized differential equation in z, because we're taking a derivative. Also, the same is true for this one. But because of these commutation relations, these two have to be proportional to each other. And the proportionality constant cannot depend on z. It can only depend on the parameter sigma. So that means that actually, so of course this depends on the omega. There has to be some proportionality constant such that these two, meaning they obey the same equation, they cannot depend on the solution can only be, it's the first order, can only be
a dependence on sigma, because that's the only, because the differential equation does not depend on sigma. So you have to have this. This exactly is the bridge equations for first order nonlinear ODE. It's basically the equation that bridges the alien calculus with regular calculus. So these are the bridge equations. How would you go to a second order linear ODE? How would this generalize? Second order linear ODE, you don't have a single parameter. It's second order, you need a parameter, you're going to have you can have two types of actions A, two types of values A in the exponentials, two parameters sigma associated with, which means that you can have, two directions, two Stokes lines, one associated with one of the A's, the other one associated with the other A, and with two parameters, sigma 1 and sigma 2. So that would be a second order, and what would happen, in fact, is that instead of this, you'd have sigma 1, sigma 2, d sigma 1 of f, plus this is S1, plus another constant, S of sigma 1 or sigma 2, d sigma 2 of f. So now you have two parameters. This would be for a second order nonlinear ODE. And then on and then on. So these are the bridge equations. Why am I doing all this work about talking about bridge equations? It's just that now this should have a Taylor series in sigma. I can, let me keep that. So my Trant series was some sigma to the n, e to the minus n a z, z to the n beta, doesn't matter, phi n. I know that my S, what are the omegas? Are NAs, so sorry, or KAs, right? So the omegas, the omega I belonging to the singularity at 0 are just the KAs, where K belongs to N. These are the singularities in the positive real axis. So my SKA of sigma, I can write it, let's write it like this. I can write it as sum SKA L sigma to the L, where L greater or equal to 0. So what do I do with this? Well, I can apply this alien derivative to f, and what does it act on? It doesn't act on the sigma, it doesn't act on the exponential, it doesn't act on the z, acts on the asymptotic series. So basically, that means that e to the minus ka z delta ka of f is going to be sum sigma n e to the minus n a z z to the n beta e to the minus k a z delta ka of phi n. That's what will give me. This one, on the other hand, will be sum L greater or equal than 0 SKA L sigma L times d sigma of this times sum n sigma n minus 1 e minus n a z z to the n beta phi n. What do I do now? Equate equal powers, sigma equate equal powers of exponentials. What are you going to find? No option, sorry. what am I writing here? It's not, sorry, just a second. It's not the Ka that's, sorry, it's the power L. So there's only a single. For each Ka, there's only a single. And now I'm now confused with my own notation, sorry. Really completely confused with my own notation because I know that is, so it's just here, the only option is so the only thing that is left is S, for K positive, so for K greater than 0, you only get the S A, and then here it's something like the 0th, or it's the 1th. You have to do this, in any case. Just equate everything, and the only thing you're going to have left is actually one single Stokes constant for K positive. For K negative, you don't. You get Stokes constants all throughout. But for K positive, you have a single one, which is what I wrote there. So when I wrote there that delta Ka phi n is Sk n plus K phi n plus K, that's exactly what you're going to find from this point of view. And what did I use? The only thing I used to see this was the fact that ddz commutes with this object, and then I can write a bridge equation. I can plug in to my Tran series. Of course, this depends on the Tran series, but I can plug it into the Tran series, and I find the exact structure that I should expect that my Borel residues will obey. So, do you think I can have 2 minutes just to write 2 equations? So what I wanted to then finish is just to write the equations that would allow you to get the large order relations. So the same way as we wrote the large order relations, we used the Cauchy's theorem to get large order relations. You can do exactly the same thing here. And now let's. Sorry, I forgot to mention. So this is the whole structure that you'd end up getting if you solve the bridge equation. So how do you go, what does phi 0 see? Phi 0 sees from the log cut phi 1 with the constant S1. Phi 1 sees phi 2 with constant 2S1. Phi 2 sees phi 3 with the constant 3S1. So they're always, it's the one that I was writing here, Sk n plus K. So you always keep on seeing it, and there's only a single S1 to go forward. But to go backwards, you have S minus 1, you have S minus 2, which connects, for example, F5 to phi 3. So there's, how do you get, for example, from phi 5 to phi 3? You can get phi 5 to phi 4, phi 4 to phi 3, or you can go directly phi 5 to phi 3 through the constant S2. And all of these, these weights and these paths, you can get directly from solving basically these equations and equating equal powers. So all of these structure you can find. And basically what you see is these lines, which was what Daniele was mentioning, because phi 0, anything that goes to phi 0 will come multiplied by 0. So it doesn't show up. So this is just a more general thing, but now what I wanted was to just write quickly 2 equations about the large order. So phi 0, phi 1 don't have anything in phi direction, but as I've mentioned here, phi 3, for example, does. So for a general phi n, so this is now large order. So what I have is now phi n. Remember that the best way to get the minus signs right is just assume x small when I'm expanding what's inside in Cauchy's theorem. And in the same way as we got the discontinuity. So for Airy, we got the discontinuity in one of the directions. Now we get a discontinuity both at 0 and at pi, because again, phi 3 also has log cuts in the pi direction. So we have 1 minus pi integral from 0 to infinity dw discontinuity at 0 of phi n divided by w minus x minus 1 over 2 pi I discontinuity of 0 to minus infinity. So in the negative real axis dw discontinuity at pi of phi n. Again, phi 0, phi 1 don't have a discontinuity in pi, w minus x. What you do, you expand this for x small. You expand 1 over w minus x for x small. And you use the discontinuities of pi, which yes, I've deleted already, but we wrote the discontinuities of at 0 and at pi as a sum over phi n plus k or phi n minus k. Those all have expansions of their own. You can expand them and then compare equal powers of x on both sides. You integrate, you compare equal powers, and let me just write, so I know that phi 0 doesn't have the pi, but let me just write what you get for phi 0. So you get an 0 for n much greater than 1. You get sum k greater or equal than 1, s1 to the k divided by 2 pi I. Again, we only have a single Stokes constant. What shows up here is not the Borel residues, but it's the Stokes constant. Gamma of n plus k beta divided by ka to the n plus k beta, sum L greater or equal than 0, ALK, gamma of n plus k beta minus L divided by gamma of n plus k beta times ka to the L. This is an expression that includes every single sector. So it's telling you what? That to first order, you get S1 over 2 pi I, factorial growth n plus k divided by a to the k n plus k. Sorry, n plus beta. N plus beta. And then you get the first sector of the first exponential, A01 plus A11 divided by n plus beta minus 1 times A, and then you get all the coefficients. But then you have higher things. So this is just the first one. What you get afterwards, you get S1 squared divided by 2 pi I, gamma of n plus 2 beta divided by 2a, it's the second exponential, n plus 2 beta. And then you get here A02 plus, etc., etc. So I just wanted to write this because I just wanted to mention, so it's not that the perturbative series sees the first exponential. No, the perturbative series sees the first exponential, sees the second exponential, sees the third, sees them all, right? They're all here. This is the first exponential. This is the second exponential. This is the third. And actually, you can use effective methods using Borel-Padé for large K, because these series are also asymptotic in large N. Large K, no, large N. So you can actually resum this a bit more or less like what I've mentioned about Borel-Padé and then Laplace resummation. You can sum this, subtract it from here, and you actually, if you did again the analysis that we've done, suddenly that singularity would disappear, and you would get these results coming from this one. So you can actually see this, meaning if you play around numerically in this case, of course, with the series. But I guess the message from this is that the perturbed series sees all of the other series. And if you did for phi 3, what would happen? It would see phi 4, phi 5, phi 6, exactly like this. But then it would also see, we would also have some gamma minus, you know, so then it would be the other way. So with a minus, here it would show up at minus Ka, because it would be in the negative real axis because of the discontinuity at pi of the previous ones. So phi 2, phi 1. So all sectors resurge in the other sectors, in the large order of the other sectors. And does resurgence. So, and I'm done, sorry. For today at least.